Hi class, welcome back to multivariable calculus. You're almost there. We're heading into the final stretch of the course. And so for the rest of the semester, we're going to be learning about path dependence, and we're going to wrap everything up with Green's theorem in a couple lectures. So we're going to start by looking at discussing path independent fields and in specific gradient fields. So for a path independent field, it does not matter what pathway you travel. All that matters is the starting point and the ending point. And then you do the same amount of work no matter what. As long as you start at the same beginning and end at the same end for a certain field, it's going to be the same amount of work done. So that would be an example of a path-independent field. So let's jump into this. So let's suppose that the gradient of f is equal to the vector field where we have just some stand-in for our x component here. We're going to call that f sub 1, and our stand-in for our y component, let's call that f sub 2. And we're going to go through the ingredients or the steps to find a potential function. So to find a potential, function, some f of x and y, we're going to need to do the following. So step 1 is to integrate it doesn't matter if you start with your x component or your y component, you just need to be consistent. I'm going to start with the x component just because that's our f sub 1, makes sense to me. You could do it either way. So we're going to integrate our x component, f sub 1, with respect to x, and then we're going to include g of y as the constant. And I'm going to put constant in quotes because it's clearly not a constant, it's a constant with respect to x, right? Just like when you take a partial derivative, any term that just has a y when you take the partial with respect to x, only you don't have to worry about, you can treat it as a constant. So we're going to include g of y as the constant. And our goal here is to integrate our vector field, right? So if we integrate the gradient of f, we can get our potential function f. So that's all that we're trying to do. So for step 2, we're going to differentiate the result with respect to y. So we're going to take the derivative of our integral here from 1. Okay, so we integrate the result we differentiate the result with respect to y, so then your g of y will become some g prime of y, the first derivative. And I didn't mean to do that. Let's see if I can zoom back in. Okay. And then for step 3, we're going to set the new result from 2 as del f over del y is equal to our f sub 2, our y component. And so the thing is, you're going to have some g prime of y in here. So for step 4, you're going to solve for g prime of y and integrate g prime of y to find g of y. Okay, and lastly, we are going to substitute g of y into our formula for f of x and y. All right, and that's it. So 5 steps. So let's try out an exercise together where we do just this. So we are going to find a potential function for the following gradient field. So let's do it for del f is, or grad f is y I hat plus x plus 2 j hat. Okay, so first we need to figure out our f sub 1, right? And so our f sub 1 is going to be y. Okay, so that's our x component. And so our first step is to integrate f sub 1 with respect to x. So we're going to integrate f1 dx, which is going to give us the integral of y dx. And so since we don't have limits here, to have the true integral, to truly evaluate this, will have to be some constant, right? So remember, we're going to include g of y for that. And so with respect to x, dx becomes, the integral of dx is x. So we're going to have yx, and our constant is g of y. So for step 2, what we're going to do is differentiate the result with respect to y. So we're going to take del over del y of y x plus g of y, and this is going to give us x plus g prime of y. And so let's take a look at f sub 2. So f sub 2, remember, is going to be equal to the coefficient, our y component, which is going to be x plus 2. So now we want to, so this is our new result is going to be equal to f2. So this is step 3. So this is going to equal x plus g prime y. And so step 4 is to solve for g prime of y. So clearly here, x is equal to x up above. So g prime of y is going to equal 2. And so then we want to integrate g prime of y to find g of y. So we got to integrate this. So 2 dy, and this is going to give us then 2y plus some constant. All right, so finally coming back around, we have that f of x and y, our potential function, is going to equal f1, or not f1, our integral of f1, right? So it's going to be yx plus our next piece, which is 2y plus c. And keep in mind that c can be anything. So on an exam, on a quiz, on your homework, you can make that c 0 if you'd like. You can leave it as c. You can give it any number you want, okay, as long as it doesn't have a variable in it. Okay, so that was one. So let's keep practicing this. And if you're feeling like you could try it on your own, definitely try this on your own first. All right, so the next one is we want to have the following gradient field. So grad f is going to be equal to our vector field, which is going to be x, y, I hat, plus 1/2 x squared plus e to the 3y j hat. Okay, so let's begin. And pause it if you want to try it on your own, of course. So f sub 1 is going to be x, y. The integral of f sub 1 dx is going to be x squared over 2y plus some g of y, and then del over del y of x squared over 2y plus g of y is going to give us x squared over 2 plus g prime y. All right, so then we want to set this equal to f2 and solve for g prime of y. So that tells us that g prime of y g prime of y is going to be, well, x squared over 2 is going to equal x squared over 2, so g prime y is going to be e to the 3y. All right, and so that tells us that we have to integrate e to the 3y dy, and that's going to give us our g of y, which is going to be equal to e to the 3y over 3. And so finally, putting these pieces together, we get that our potential function is going to be equal to 1/2 x squared y plus 1/3 e to the 3y. Okay, and notice that the potential function is not a vector, right? But the gradient field is a vector. And we can have any constant we want at the end. I'm going to use 0 in that case. Okay, so moving on, let's keep trying some. So here's another. We're going to find a potential function for grad f is equal to cosine y rid of that. Sorry about that. Cosine y plus y squared plus 3x squared I hat plus minus x sine y plus 2yx plus 2y j hat. Bringing out the big guns on this one. So this one is a little more complicated. So let's first set f1. Okay, so that's going to be cosine y plus y squared plus 3x squared. And so if we integrate that, with respect to x, we get x cosine y plus x y squared plus 3x cubed over 3, so just x cubed, plus some g of y. So then the next step is to differentiate with respect to y. So del over del y of x cosine y plus xy squared plus x cubed plus g of y. All right, and so this is going to give us minus x sine y plus 2xy plus x cubed becomes 0, so plus g prime of y. And so this is going to give us then, well, look how nice this is. So that matches up with this first piece of our y component. So that tells us that g prime of y is going to be equal to 2y. So then if we integrate 2y with respect to y, we're going to get y squared plus a constant. And then putting our final pieces together, we get that our potential function is x cosine y plus y squared x plus x cubed plus y squared plus whatever you want to make your constant. Once again, I'm just going to make it 0. All right, there goes another. So let's try something a little different. All right, so last class, we found the work done by the following vector field in moving a particle along a circular helix. And the time interval on that was, the circular helix is given by the position vector, right? R of t is equal to cosine t I hat plus sine t j hat, and to make it a helix we have t k hat, where our time interval is from 0 to pi. All right, and we did that by calculating the line integral. Right, so that gives us the work. And the dot product between our vector field and dr. And so the last piece was we had our field was equal to 2x I hat plus 3y j hat plus z k hat. Okay. So this is our vector field F. So we want to recalculate the work done using the fundamental theorem for line integrals. And so for the rest of this lecture, I'm going to call the fundamental theorem for line integrals FTLI, because that is a really long name. Okay, so to do this, well, the fundamental theorem of line integrals says that the work, or the line integral, of f dot dr is going to equal the potential function at our endpoint. Well, actually, I stepped one step ahead for a sec, so let's back up. So the line integral over C, whatever our path is going to be our gradient field dotted with dr. Okay, and so technically that is going to be the same as, since it's path independent, we were talking about that earlier, as evaluating our potential function at our endpoint. We're going to say our endpoint is Q minus our starting point, and that's it, and that'll give us the work. So let's talk about one way we can do this. So step one would be find a potential function f of x, y, and z such that grad f is equal to our field, our vector field. So in order for it to be a gradient field. Okay, well, let's look at what we have. So we have 2xi hat plus 3yj hat plus zk hat. So the nice thing about this example is our x component is in terms of x, our y component is in terms of y, and our z component is in terms of z. We have no mixed variables in any component. So it's pretty straightforward actually to guess what a possible potential function could be for this field. So for this component, our x component, a good guess would be, well, the integral of 2x dx, which gives us x squared. And if we did the same then for 3y, we get 3y squared over 2 when we integrate that. And then if we integrate z with respect to z, we get z squared over 2. Okay, and then then if we check that, right, take the partial with respect to x, we do in fact get 2x I hat. Partial with respect to y, we do get 3y j hat. Partial with respect to z, we do get z k hat. Okay, so that works. Step 2. We're going to find starting point P and ending point Q of the curve C. So we were given our position parametric function as a function of our position vector as a function of time. And so now we're going to have to convert it to coordinates by evaluating, well, we started at a time of 0. So what was our position at time of 0? We ended at time of pi. What was our position at pi? So our starting point, P, is going to equal, well, if we take cosine 0 for our x component, that gives us 1. If we have sine of 0 for a y component, that gives us 0. And then we also get 0 for our z component. And then our ending point Q is going to be, well, cosine of pi is going to be -1. Sine of pi is 0. And then we plug in pi for t, and we just get pi. So we have our starting point and our ending point. Okay, so then step 3, our final step, is going to be to calculate the work done using the fundamental theorem of line integrals written above. So that tells us that the line integral, or the work here over C of f dot dr, is going to be f at our ending point minus f at our beginning point. And this f, of course, is our potential function. And so for us, it's going to be f at -1, 0, pi minus f at 1, 0, 0. All right, so let's plug this in. So f of -1, 0, pi is going to give us, well, -1 squared is 1. And 0, anything is 0. And so then we have pi squared over 2. Then we're going to subtract off. Let's see. So then we have 1, 0, 0. So 1 squared is 1. All right, and that's going to be it there. And this is going to give us pi squared over 2. And if you look back, we did solve this problem last class, and we got the same result, pi squared over 2. So for this one, because it is path independent, you can find the work done using either the fundamental theorem of line integrals or its more standard definition that we used last class. Okay, let's keep going. Now let's calculate the work done dealing with the same problem by the vector field and moving a particle from 0, 0, 1. Did I already do that? No. Just kidding. We're given points now. Calculate the work done by the vector field in moving the particle from 0, 0, 0 to 1, 1, 1. All right, so for this, we already found our potential function. So it's just going to be using the fundamental theorem of line integrals over a different path. Well, it's different starting point, different ending point. So it should be different work done. And that's going to be our potential function at 1, 1, 1 minus our potential function evaluated at 0, 0, 0. And so if we plug it in, we end up getting 1 plus 3 over 2 plus 1/2 minus 0. And this will give us 3. Okay, last part. Is the vector field path independent? So I've said this many times throughout this problem. Yes. Yes, it is path independent. Okay, so, and it is path independent since there exists, that's this backwards E, a potential function f such that the gradient of f is equal to our field, our vector field, making it a gradient vector field, which is path independent. Okay, let's go through one more. All right, so last class, we also found the following. So we also found the line integral for the following vector field, which is going to be vector f along a parabola from 1, 1 to 2, 4. Okay, so this was a position 1, 1 to position 2, 4. And we had f is equal to x, y, I hat plus x, j hat. And we're moving it along y equals x squared from 1, 1 to 2, 4. So we're going to try to use the fundamental theorem of line integrals to calculate this. And so I want you to give this a pause, try it on your own first before proceeding. So let's start by trying to find a potential function such that our vector field is equal to our grad of f. So let's just use some of the steps from before. So there we go. So let's say that f sub 1 then is xy. So the integral of xy dx is going to be x squared over 2y plus g of y. And so then the partial derivative with respect to y of x squared over 2y plus g prime of y is going to be equal to, so with respect to y, we get x squared over 2. And I should not have put that prime in, plus g prime of y. So we need to try to solve for g prime of y by saying, okay, well, f sub 2 is equal to x, which is equal to this, which is x squared over 2 plus g prime of y. All right, so the problem here is there's not a case where x is equal to x squared over 2. That can't be. And so we can't solve for this. So this is not equal to our f2, which is x. All right, so it doesn't work. We can't find that potential function. Okay, so here's where this is our hiccup right here. So if f is a potential function for the following vector field, which is still going to be xy I hat plus xj hat, then the gradient of the field is, so let's go through that. So the gradient of the field is grad f is equal to xy I hat plus xj hat, right? So in this case, it tells us that the partial derivative with respect to x is going to be xy, right? Definition of gradient function. And our partial derivative with respect to y is going to be x, okay, which is just our f sub 1 and our f sub 2. So now let's try out something else to see if, well, is there a way to find a potential function? Is there any way this would work? So one thing we can do is we can use the fact that the mixed partials, so we're going to look at the second order partials. So f with respect to x followed by with respect to y should be equal f sub yx, right? We know those should be equal to each other. So we're going to use the fact that those should be equal to show that there is no potential function for our vector field f. So in other words, our vector field f is not the gradient of any function of f. There does not exist a potential function for it, right? So f sub xy should equal f sub yx if, in fact, there is some potential function that exists for this field. So let's give it a shot. So we have our first order partials all set. And so f sub xy then is going to be xy then taken with respect to y. And that is going to give us del over del y of xy is equal to x. And then the same thing for f of yx is going to equal the partial derivative with respect to x of x, which is going to give us 1. And it is clear that x does not equal 1. Okay, so there does not exist a potential function. Okay, let's explore this a little bit deeper here before we wrap up for this lecture. So let's keep going. Oh no, I didn't mean to do that. Sure. There we go. So let's keep going. Okay, so previously we have found in a different lecture that for f, the vector field f equal to x, y, I hat plus x, j hat, the line integral over some curve, and I'm going to call that curve C1 of f dotted with dr, so the work, is 101 over 12 when our curve C sub 1 was the parabola from 1, 1 to 2, 4. And we have also found that for the same gradient field, or sorry, for the same field, for the same vector field, over another curve, we found that that was 17 over 2 when C sub 2, this other curve, was the line segment from 1, 1 to 2, 4. So even though they have the same starting point, the same ending point for the same vector field, we know that this is not a path-independent vector field. It's not a gradient field. So this is a path-dependent field, which we're going to get into a little deeper in the upcoming lectures. And so one more part here that we're going to look at. So I want you to just think about why these results from part C tell us we can't use the fundamental theorem of line integrals to calculate the line integral f dot dr for these two, across these two different curves, right? And that is because part C is not path independent, which tells us it is not a gradient field. So in other words, the potential function f does not exist. So a vector field, so the vector field is path dependent. Therefore, the vector field f is x, y, I hat plus x, j hat is path dependent. All right. So we are going to talk about path dependence, really short lecture next time. And then finally, we're going to learn how to evaluate that using Green's theorem in our final lecture of the semester. So I'll see you next time. Take care.